Hello everyone, greetings. My name is Verde Orbusto, and this is actually Thursday. We're now on Thursday the 30th of July, 2020, if I'm not mistaken. And this is the Schumann Resonance Harmonics channel. Thank you all for being here. You're giving me a reason to get onto the internet and to deliver a positive message. Okay, so today's session is about the ringing in the ears. The ringing in the ears. This has been a multi-part session, and I wanted to go over a few different items that I'm working through comments with people and things. It gives me ideas to kind of focus on as we're moving forward. But the biggest problem is the ringing in the ears, and people are saying all sorts of things about it. But I want to examine this from the perspective of the Schumann resonances. Okay. Once again, if you have a medical condition, you got to go see a doctor. Okay. I'm not here to address medical issues. If there's something legitimately wrong, you got to go see a doctor. That's not what this is. What this particular series about the ringing in the ears is about when you've gone to see a doctor, there's nothing they can do about it. Number one, I'm not a doctor. I'm not going to treat anything. But I am going to give you some things to think about at this point, if you've ruled tinnitus out with a capital T, but there's still a ringing in your ears, I'm going to address that, as well as the vertigo. As we have seen in the past, there is a correlation between the two. So the first thing on my title page here, I have a illustration of the ear, the working of the ear, and then right next to it, this is a induction coil. So what I'm suggesting is that the inner ear, the cochlea, this part here, the cochlea, is a coil. Okay, you can see it. Now, as we go on and we explore this, sorry, I'm moving my light here. You will be able to see the similarities and the correlation of what I'm talking about. Okay. So this is a little diagram of how the ear works. Okay. How the ear works normally. Okay. Sound is transmitted as the waves. All right. Let me actually go to the type. All right. So this is courtesy of umms.org, and I will have the link in the University of Maryland Medical Center. If you can see that up there. All right. Up there somewhere here. All right. Okay. So this is basically how the ear works. All right. So you see sound. All right. So the going one. Sound is transmitted as waves from the environment. The sound waves are gathered by the outer ear, okay, this here, and sent down the drum, the ear canal, to the eardrum. All right, so the waves collect here, it's sent down to the tympanic membrane. That's what this is. Two, the sound waves cause the eardrum to vibrate, which sets the three tiny bones in the middle ear into motion. So they're showing you 1, 2, 3. This is the number 2 on the diagram. Then the next one, the motion of the bones causes the fluid in the outer ear, or the inner ear or cochlea to move. All right, so the movement caused by these, they're vibrating in fluid. Okay, so it's under pressure. It's in a fluidic medium. So sound needs a medium to travel through. Sound and audio are compression waves. So unless a medium is compressed, you don't hear it. Okay? So the movement in the inner ear fluid causes, the motion of the bones causes the fluid of the inner ear cochlea to move. Number 4, the movement of the inner ear fluid causes the hair cells in the cochlea to bend. The hair cells change the movement into electrical impulses. So 4. So that's where we're at here. So the movement, so it's like a drum. The movement causes there to be an electrical signal. Okay? The hair cells change the movement into electrical pulses. These electrical impulses are transmitted to the hearing auditory nerve and up to the brain where they are interpreted as sound. Okay, so I'm going to show you a picture of the hair cells. Okay, so I'm showing you the hair cells. Now I realize you can't see the top of the picture here. There's a little bit missing, but that's all right. We don't need that. So this right here are the hairs that they're talking about, okay? Inside of the cochlea, or the inner ear, this little coil here, lining the coil are these hairs, the damaged hairs inside the cochlea. Now we're going back to tinnitus can be caused by broken or damaged hairs on auditory cells, turbulence in a carotid artery or jugular vein, temporomandibular joint, TMJ issues, and the problems in the auditory processing pathways of the brain. Okay, so these hairs, once again, these hairs create an electrical signal that goes into the brain as sound. And what we have found here, okay, is that you can get, because of that, those hairs being messed up, you would get, may include these types of phantom symptoms. So tinnitus is not just a ringing in the ears, it's also a buzzing in the ears. It can be a roaring in the ears, a clicking in the ears, a hissing in the ears, a humming in the ears. So it can be, and is, a number of different things here, which makes sense if you remember the old stylus needles, if you've ever rubbed your finger on it, you would get that that kind of scraping sound. And these are humming, the clicking, hissing, buzzing. These are all sounds that you hear related to electricity, especially the buzzing, the hissing, the humming. Power lines will create this kind of hum at 60 hertz that you hear. It also says the phantom noises may vary in pitch from a low roar to a high squeal, blase, blase. Okay, so we've been through this already. All right, now, and we're ruling out tinnitus as the cause of the high-pitched ringing. All right. Okay. All right, so we've gone through how the ear works, generally speaking, the ear works, and there's this coil here which translates the signal on the inside of the cochlea have those hairs. So this here is translating those electrical impulses down this electrical wire which goes to the brain. This 5 that's our electrical impulses are transmitted to the hearing auditory nerve and up to the brain, where they are interpreted as sound. Okay. Now, let's look at something here. All right. Where am I? I'm going to pause this here. Okay, so this is not the most glamorous looking picture here. There's a lot of white space, and I apologize. It's kind of difficult to do what I need to do. All right, so this is an antique induction coil. Let's see if I can scoot in on it. All right, there's 2 here. All right, so you get the basic gist of this and the other one. This was the one that was in the illustration here. All right, so it says an antique induction coil used in schools from around 1900 in Bremerhaven, Germany. And this is an induction coil showing construction from 1920. And then we have, this is the schematic diagram of our induction coil. All right. Now, I'm going to read to you what it says. This is Wikipedia. All right. zoom out. Okay, so this is a page of text. It's not too glamorous. All right, so I'm just going to read what it says about induction coil. An induction coil, or spark coil, archaically known as an inductorium or a Ruhmkorff coil, after Heinrich Ruhmkorff, excuse me, is a type of electrical transformer. All right, an induction coil is a type of electrical transformer, okay, used to produce high voltage pulses from a low voltage direct current DC supply to create the flux changes necessary to induce voltage in the secondary coil. The direct coil and in the primary coil, did I read that? Direct current in the primary coil is repeatedly interrupted by a vibrating mechanical contact called an interruptor. Invented in 1836 by Nicholas Callan, with additional research by Charles Grafton Page and others. The induction coil was the first type of transformer. Again, the induction coil was the first type of transformer. It was widely used in X-ray machines, spark gap radio transmitters, arc lightning, and quack medical electrotherapy devices from the 1880s to the 1920s. Today, its only common use is as the ignition coils in internal combustion engines and in physics education to demonstrate induction. So, electronic ignition uses an induction coil. All right. Okay. Construction and function. All right. So let me just say, I'm not expecting anyone to get what all of this is right first time you get it. So please don't say, well, I have a dumb question. You kind of went through this, you breezed through it, and I didn't get it. I'm introducing this, and I want to have a discussion on this, but I got to start somewhere. So I want to have a kind of cohesive understanding of how these things fit together, and then tighten up the definitions on it to working definitions so that we all have a lexicon of commonly understood words and usage. In my opinion, the problem with communication is not the vocabulary. The problem in communication is having a shared vocabulary, that we all know what the meanings of these certain words are as relating to the Schumann resonance harmonics, period. Okay. So in all cases, I am giving you the words and the definitions based on their relationship to the Schumann harmonics or Schumann resonance harmonics, electromagnetic frequency standing waves that we're seeing on the Schumann graphs. All right. So that's kind of a disclaimer for this lesson today. All right. So let me go back to reading to you what it says. An induction coil consists of two coils of insulated wire wound around a common iron core, which is represented by the letter M in their equation. One coil, called the primary winding, letter P, is made from relatively few tens or hundreds turns of coarse wire. The outer coil, the secondary winding, S, typically consists of up to 1,000,000 turns of fine wire, up to 40 gauge. Again, 1,000,000 turns of fine wire. An electric current is passed through the primary, creating a magnetic field. Because of the common core, most of the primary's magnetic field couples with the secondary winding. All right, let's make sure I got this right. The primary behaves as an inductor, storing energy in the associated magnetic field. When the primary current is suddenly interrupted, the magnetic field rapidly collapses. This causes a high voltage pulse to be developed across the secondary terminals through electromagnetic induction. Because of the large number of turns in the secondary coil, the secondary voltage pulse is typically many thousands of volts. This voltage is often sufficient to cause an electric spark to jump across an air gap, represented by G, separating the secondary's output terminals. For this reason, induction coils were called spark coils. An induction coil is traditionally characterized by the length of spark it can produce. A 4-inch, 10-centimeter induction coil could produce a 4-inch spark. Until the development of the cathode ray oscilloscope, this was the most reliable measurement of peak voltage of such asymmetric waveforms. The relationship between spark length and voltage is linear within a wide range. 4 inches, 10 centimeters equals 110 kilovolts. 8 inches, or 20 centimeters, equals 150 kilovolts. 12 inches, 30 centimeters, equals 190 kilovolts. And 16 inches, or 41 centimeters, equals 230 kilovolts. All right, so curves supplied to the modern reference agree closely with those values. All right. Okay, so it magically transported us here to the Schumann, the reason for us being here. Okay. Let's see. I'm going to zoom in. All right. Whoop, a little too much. All right. All right, so these are our resonances here, over on this side. Let's get organized. All right, so this is the 20. This is upside down, in case you haven't noticed. All right, so everything's upside down. So when I do the Schumann reports, I have this upside down, okay? So this is 0, that's 4, that's 8, that's 21, or 16 rather, that's 20, that's 24, that's 28. All right, so this is our magical coded line at 25 hertz. This is our magical coded line at 17 hertz. This is our magical harp line at 2. I'm saying the harp isn't interfering with the Schumann, but here we can show, I have shown, harp operates at 2 hertz. So this right here, this would be 3 hertz, approximately 3 hertz. Let's just say this area here is what harp does. Nothing else is, all right. So this right here, I'm pretty sure this is the local train station here. And I'm pretty sure because how thin this line is, that this is local interference as well. All right. So these thin lines would be, these are not waves. This is a line. This shows there's some electric content to it. There's obviously, this is 3 kilovolts standard on the trains. All right. So what I'm going to point out here, we were just talking about magnetic induction. All right. So oh, look at this. Wow. Wow, 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 wow. This is a broad range of waves here from 2 up to about 9. This is here about 9, 10, 10. From 2 to 10. So this is 8 hertz bandwidth here of this crazy wave here. This is an unusual occurrence here. These relatively narrower band of this harmonic. This is a 7.8 harmonic. This is going some crazy. I'm not sure what's going on here. But you see this, also, you can't... All right, it's off the thing. All right, so where I'm going with this, what am I talking about? All right, so this right here is magnetics. Okay, this is picked up by the induction coil of the Schumann antennas. It's really important to know this. This is the mid-grade. You have the oranges, you have the rust, you have the red. This is mid-grade magnetics and electrics tumbled together. Okay? So the electrics move this way, bing, bing, bing. They're uprights. These are the amplitude spikes. All of these uprights are amplitudes. All of these horizontals are magnetics. Bing, bing. The waves, the frequency waves here. Okay. So when we're talking about magnetic induction, we're talking about not sound waves hitting that fluid in your ear and moving those, the bones, okay? Audio compression waves will compress that medium and it will turn into a vibration, which, like that, which gets translated into an electrical signal and sent to your brain, okay? So the compressible medium of that fluid has produced a compression wave of sound. That is not what magnetic induction is. Magnetic induction is how do I put this? We've already been through what it is. It's taking a electrical signal and in creating it does two things. Creating an electrical signal from magnetism in the atmosphere, or it takes a magnetic signal wrapped around the coil and produces electricity. So one or the other happens. You put magnetism in the coil, you get electricity. Or, in the case of an electromagnet, you have a coil, you electrify it, you produce a magnet. Okay? So these are two sides of the same coin, if you will, that depending what you put in is what you'll get out. So the high-pitched frequencies are not audio. It's not a compressible medium. This is a magnetic induction, which was caused by the electric signal, which creates sound, is caused by the magnetism of the environment around us. And this is what I'm showing you here. These are not the heavy green lines. This is magnetism and electricity. These mid-grades here floating around are sticky to the incoming electricity. Bing, 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 bing. So that if it was just the magnetics, it would have already been like the green, the heavy green, the bright green. This is not bright green. This is like yellow. We got yellows in here, little speckles of see in here, little speckles of rust. But this is turquoise and teal. This is not the green mode. You can see green here. It's hard to even see. Like, there's really not that much green on here. Like a little bit around here. And even then still, I'm curious, as I'm questioning whether that's the true green mode. When I talk about green, like the bright green, I'm talking about mode 4, which is the heaviest of the magnetics, and it's the widest of the electric. Okay, so I'm almost at 25 minutes here. I've gone through everything I needed to. I explained the basic premise and how I'm getting at the fact that it's these frequencies are not the high-pitched frequencies that people are hearing are not sound. It is not a compressible medium. Otherwise, you'd be able to pick that up in the environment. Tinnitus, as you know, or as we've gone through, it is a individual malady that affects only you or the sufferer because of the hairs, the bent hairs on the head, the ear. Okay, so with that said, because there's so many people that are going through this, it could not be one single person having that ringing. And there is not one single person having that ringing. Tinnitus will, again, also come up with other symptoms that go with it, like the cracking, the buzzing, the things you would expect from a loose electrical connection. Tinnitus is, in my view, it is a loose electrical connection, which are those bent hairs that do not transmit the signal properly. So it's like a bent wire or a bent antenna. Like, I think that's a better way to put it, that those hairs are like little antennas on the inside of your cochleal wall. And so with the high-pitched frequencies, I would expect that if it's tinnitus, you're going to get other things with it. You're going to get other sounds as well, okay? Whereas if it is, as my theory holds correct, the magnetic induction, you're going to get a single steady pitch. You won't get crackling. You won't get the buzzing. You won't get any of that because the connections themselves are good. In the magnetic induction model, as I said, the hairs would be all fine. Everything would be, in fact, it would have to be fine in order for you to be getting those magnetically induced signals coming through the environment. So this is basically just a basic overview of how the magnetic induction relates to the Schumann harmonics. This, what I'm calling indigo. All right, so just really quick. These vertical bands here, these are the resonance harmonics. Okay. These are, that's your 7.83 that's not ever changing. This is your 14.4 that's not going to be changing. This is your 22.2 that's not ever changing. Or it's 21, I guess, closer to 21. I like calling it 22, even though it's not really correct. And this is your 27. Or 26, yeah, like 26, all right. So 24 is here, 28 is there. So in the middle of that is like 26, all right. But look at how the frequencies are not rising, but the bandwidth is increasing. That's important to notice. The frequency itself, you're always going to get almost 8. That's not ever going away. That's not ever changing. It's even behind that. Ding, ding, ding. This frequency here of the 14.4, that's not ever going to be going away. This isn't going away. That's not going away. It's not rising. Otherwise, it would not be at 8. It would be up here. Right? So these frequencies are constant because the size of the planet is constant. The speed of light is constant. The fact we are on a globe is constant. Okay, so all of this, like 10 years ago, that wasn't there. Occasionally you'd see this, but it wasn't developed like this. It was more the green. It was much more green, and it was not as wide as this. Okay, so the upper harmonics, this one here, at at 17, so 20, around 20. You can see it, 18, 19, 20, somewhere around there. So that stays the same. But you're seeing these more in action or more active than they ever were. And it is because these free-floating magnetics, the free-floating electrics in our environment are causing this ringing and other problems. One of those other problems is the vertigo, and I will be discussing that in the next video. Okay, so this is almost half an hour. It's probably a good place to stop for today. These videos keep getting successively longer, even though I'm not wanting them necessarily to be. All right, so thank you all for being here today, and I appreciate you coming here to help me learn about the Schumann resonances, and I appreciate the comments and the feedback. Thank you for all the subscribers. Thank you very much to Wayne's World for showing light on this pathway and for showing light on and love on my YouTube channel. So thank you all for being here, and I appreciate your coming here to help me learn more about the resonances. And everyone have a great rest of your day. Thank you for being here. Namaste.